Hello people, so this is the second problem in the AP free response practice number 3. Let's look at it closely and try to analyze what is going on. Let me read it for you. An Atwood machine consists of two blocks connected by a light string that passes over a frictionless pulley of negligible mass, as shown in the figure above. The masses of the two blocks, M1 and M2, can be varied. M2 is always greater than M1. On the dots below, which represent the blocks, draw and label the forces, not components, that act on the blocks. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. The relative lengths of the arrows should show the relative magnitudes of the forces. So, they tell you that M1 is always less than M2. Therefore, when you draw your forces here, you should be considering that the length of the force should be indicative of relative lengths. For example, you can draw the gravitational force M1G like this, and then the gravitational force M2G much larger like this, because if this is going to accelerate, given that M1 is less than M2, then M1 is going to accelerate upward. And that can only happen if the tension on the string is greater than M1G. But also, M2 is going to accelerate downwards, so the tension on the string should be less than M2G. Therefore, M1 is less than the tension, M2 is larger than the tension, and the two tensions are equal because they form an interaction pair according to Newton's third law. So these are the free body diagrams for each of the masses. B. Using the forces in your diagrams above, write an equation applying Newton's second law to each block and use these equations to derive the magnitude of the acceleration of the blocks and show that it is given by the equation A equals M2 minus M1 over M1 plus M2 times the gravitational acceleration G. So, in this case, you are requested to use Newton's second law on each of the objects. Now remember, given that M1 is less than M2, then mass 1 is always to accelerate upward. Therefore, what you have is that if you pick up to be positive, the tension minus M1G is going to be equal to M1 times acceleration. But then M2 is going to accelerate downward. And so the equation for that block is going to be M2G minus T is equal to M2A. So that the acceleration is positive on both cases. Upward for M1, downward for M2. Now, when you combine these two, given that the tension is an interaction pair, they're going to cancel out. And what you have on the left-hand side is the difference, M2G minus M1G, and on the right-hand side, the addition or sum, M1A plus M2A. Now you can take a common factor of both sides, and on the left hand side you have M2 minus M1 times G. On the right hand side you have M1 plus M2 times A. So a little algebra tells you that the acceleration is given by the fraction M2 minus M1, which is the difference in masses, over M1 plus M2, which is the total mass of the system, times the gravitational acceleration G. This is, of course, the formula proposed over here, and so you have proven the fact. Now, the next part gives you some laboratory data. It says that the magnitude of the acceleration A was measured for different values of M1 and M2, and the data are shown below. So you have different masses, different values. You can see that, just as they said at the beginning of the problem, M1 is always smaller than M2, and then you have a measured acceleration for each case. and they want you to indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity g. Now, if you use the formula given in part B, acceleration equals to g times the difference m2 minus m1 over m1 plus m2, you can notice that this has a lot of similarity with your familiar equation y equals m times x. The whole idea is, if you take this approach, the acceleration can be thought of as the variable on the vertical axis, and then on the horizontal axis, you can take the quantity m2 minus m1 over m1 plus m2, which is also variable because the two masses are varying, okay? So the g, which is a constant, basically is the slope of this line. So you can get the value of the gravitational acceleration by getting the slope of this straight line. So on the vertical axis, you want to put the acceleration a. On the horizontal axis, you want to put the quotient between the difference of the masses over the total mass m1 plus m2. Now, if you make the calculations, you're gonna get several interesting values whenever you substitute m1 and m2. And we have done the work for you. So if you substitute these values, you get, in the first case, 0.33, in the second case, 0.20, third case, 0.41, for the fourth trial, you have 0.14, and for the last, 0.70. Now, once you have these values and the values for acceleration, you can come over here and do as they are given. The request is plot the data points for the quantities indicated in part C on the graph below. Clearly, scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. So you have the acceleration over here in meters per second squared. It's easy to see that your values have a maximum of 4.21. So a good scale would be to start out with 0, 1, 2, 3, 4, and 5. And so each little division is 0.2 meters per second squared. Then on the horizontal axis, you have the quantity m2 minus m1 over m1 plus m2, and this has no units because the numerator has kilograms, the denominator has kilograms, so this doesn't have any dimensions. Now, the quantities go up to 0.41, therefore, you want to go with much smaller numbers here, like 0.10, 0.20, 0.30, 0.40, and so in this case, each division is 0.02 of this quantity. Okay, so 0.02, 0.04, 0.06, 0.08, 0.10, and so on. So the very first point that we have is 0.33, 3.02. 0.33 is over here. 3.02 is somewhere around this position. Next is 0.20, 1.82. 0.20, 1.82. Next, 0.41, 4.21. That will be over here. Then we have 0.14, 1.15, and that will be around here, and finally 0.17 and 1.71. So that will be somewhere over here. So you can see that all these points are, of course, approximately on a straight line. Now, it's always a good idea to take a close approximation to all the points, and so we're going to insert a line this way. Let's take the alignment carefully. Now remember, whenever you take a measurement for a best fit line, the idea is to have the line as close as possible to all the points, with some points below and some points above your line, sort of like this. And then once you have your line like this, they ask, using your straight line, determine an experimental value for G. Now you might remember that in our model we decided that G was going to be the slope of that line. So all we need to find is what is the slope for this line, blue line that we just drew. Now remember that it's very important that you do not take points that are outside of your line. So these two could be good approximations. This first point is 0.34, 3.4, and then the second point, lower over here, is 0.16, 1.4, and so those are 2 points to get the slope of. That slope is going to be equal to the gravitational acceleration, and that's going to be 3.4 minus 1.4 divided by 0.34 minus 0.16. When you take that division or quotient, you get the following: 2.0 divided by 0.18, which gives you the result, 2 divided 0.18, 11.1 meters per second squared, which is sort of accurate. It has approximately a 10 or 12% error, but that's okay. You just have to be careful that as long as your line is more or less aligned, you should have no problems with that answer. Finally, they request something of a deep understanding question here. They tell you that the experiment is now repeated with a modification. The Atwood machine is now set up so that the block of mass M1 is on a smooth horizontal table, and the block of mass M2 is hanging over the side of the table, as shown in the figure. For the same values of M1 and M2 is the magnitude of the tension in the string when the blocks are moving, higher, lower, or equal to the magnitude of the tension in the string when the blocks are moving in the first experiment. Now, what you have to consider here is, first, are you going to have a larger or a smaller acceleration in this case? If you think about the objects, M1 and M2, and their free body diagrams, you might consider the idea that in the second case, there is a tension here, but there is no force preventing M1 from accelerating. In this case, the gravitational acceleration m1g is cancelled with the normal force from the table. So only the tension is accelerating this object, therefore you should have an acceleration that is larger in magnitude than the one in the first trial when the two blocks were hanging. So this acceleration should be larger, and therefore the acceleration for m2 should also be larger. Now in the case of m2, you have the same tension m2g, the same gravitational force, but then the tension, if you have a larger acceleration, this means that m2g minus the tension is also larger. And if the difference between the forces is larger, well, m2g cannot have changed. Therefore, the tension has to be smaller. So, the tension in the string should be lower, and your answer over here is lower. Finally, they ask you, the value determined for the acceleration due to gravity, g, is lower than in the first experiment. Give one physical factor that could account for this lower value and explain why this factor affected the experiment. Now, there are two physically reasonable ideas here. The first one is that there is friction. If there is some friction with the table, then the values for A are going to be lower. And that means that instead of having a set of points that look like this, you are going to have a set of points that looks like this. And in that case, if you have lower values for A, you're gonna have a lower G. So that's one option. The second option is that maybe the table is slanted to the left. Because if you have a little inclination so that the left side is lower than the right side, then there is going to be some component of the gravitational force pulling on M1 to the left. And in that case, your model has a mistake because you're only assuming that there is a tension over here and there is no force pulling backward. So in that case, once again, you are going to have a lower value for each acceleration and therefore a lower slope. So those are the two possible ideas that you can argue for why you are getting G as a lower value than in the first experiment. So make sure please that you look at the scoring guideline and study this problem. Thank you very much for your attention. See you later.